Welcome to the HL-HSPC Lenticular Aerospace Craft Program, led by James Hartman, Hybrid Innovator and Propulsion Designer. This program formalizes a revolutionary propulsion architecture, integrating mass-modulation physics, hybrid resonance systems, and advanced metamaterial engineering. The lenticular craft is not just a vehicle, it's a flying laboratory, designed to test and demonstrate the internal theory behind field propulsion. Our mission is twofold. First, to develop a fully instrumented aerospace platform capable of controlled mass-modulated flight. Second, to establish a repeatable engineering framework for next-generation field propulsion vehicles. Every aspect of this program is grounded in disciplined engineering and rigorous internal physics. HL-HSPC's mission architecture is built on a foundation of quantum wire capacitance technologies, thermoquantum field transduction, tunable inertial-coupling systems, high-frequency gravity-resonant engines, metamaterial field shaping surfaces, and spintronics-based control logic. These elements work together to create a platform that can demonstrate controlled mass-modulated flight. The craft is designed for a broad operational envelope, including low-altitude hover, high-agility maneuvering, high-altitude flight, and near-space resonance mode operation. Every subsystem is part of a unified architecture, ensuring seamless integration and operational excellence. The heart of the HL-HSPC program is an internal theoretical framework that unifies electromagnetic stress fields, thermal gradient transduction, acoustic electromagnetic resonance, spintronic phase control, and mass coupling modulation. These are not speculative concepts, they are established engineering principles, validated through controlled bench experiments, resonant cavity diagnostics, low-torque capacitor discharge studies, and noble gas sonoluminescent collapse tests. This internal theory provides the mathematical and operational backbone for all HL-HSPC subsystems, ensuring every component operates in harmony. Lenticular craft is the fourth major iteration in a lineage of hybrid field propulsion demonstrators. Its design philosophy emphasizes symmetry for field coherence, modularity for rapid subsystem replacement, redundancy for safe experimental operation, transparency for diagnostic clarity, and scalability for future multi-role platforms. Lenticular geometry is not just aesthetic, it's functional, supporting toroidal field formation, distributed resonant cavities, uniform M-carrier layers, stable mass-void shaping, and omnidirectional maneuvering. This shape is deeply aligned with the internal theory, making it the optimal choice for HL-HSPC's mission. HL-HSPC craft is engineered for a wide range of operational scenarios. It can hover at low altitudes, perform high-agility lateral maneuvers, fly at high altitudes in low-density environments, and operate in near-space resonance modes. The platform supports experimental propulsion cycles, inertial mass modulation tests, field geometry mapping, autonomous resonance tuning, and high-bandwidth telemetry collection. As a flying laboratory, it validates the internal theory through controlled, instrumented flight, pushing the boundaries of what's possible in aerospace propulsion. HL-HSPC program is defined by disciplined engineering, rigorous internal physics, transparent documentation, modular experimentation, and continuous refinement. Every subsystem, schematic, and field flow model is part of a unified architecture under the leadership of James Hartman. This identity is reflected in every aspect of the program, from design to operation, ensuring that the HL-HSPC remains at the forefront of aerospace innovation. The signature line of James Hartman anchors the program, symbolizing its commitment to excellence and innovation. HL-HSPC platform features a 20-meter diameter by 7-meter tall lenticular craft with a central dome and a tapered ventral profile. This global geometry is meticulously defined to support toroidal field formation, symmetric mass-void shaping, distributed resonant cavities, and omnidirectional maneuvering. Lenticular form is not merely cosmetic. It is the enabling geometry for the program's gravity-resonant and M-carrier field architecture, ensuring optimal performance and stability during all flight modes. The primary structure of the HL-HSPC is a radial rib network, typically represented as a 26-segment truss system, extending from the central column to the outer hull. These ribs carry vertical and lateral loads, maintain geometric fidelity under high-frequency vibration, and provide mounting interfaces for resonators, capacitor banks, and decks. Acting as resonance conduits aligned with internal field nodes, the ribs connect to a central midline ring, which serves as the main structural interface between the central resonator column, capacitor annulus, and internal platforms. Structural skeleton employs a hybrid frame of carbon nanotube, CNT, trusses, and Ni-Ti-based memory metal actuators. This combination provides an exceptionally high strength-to-weight ratio and dynamic tensioning for shape control. Triaxial ribbing prevents torsional deformation, while memory metal elements adjust preload and alignment to keep resonant subsystems in phase. The frame supports precise positioning of QWCL plates, thermoquantum modules, and capacitor banks, acting as an active structural resonator for the entire craft. Internally, the HL-HSPC hull is divided into functional zones: the upper dome for command and sensors, the mid-deck for systems and resonators, and the lower deck for pulse power and capacitor banks. Service bays and modular pods occupy the annular regions between ribs, enabling rapid subsystem swap-out, instrumentation upgrades, and future experimental modules. This zoning ensures that each subsystem is optimally placed for performance, maintenance, and future scalability. External surface of the HL-HSPC is composed of segmented metamaterial tiles, each capable of tuning effective permittivity, permeability, emissivity, and reflectivity. These tiles anchor directly into the rib network and interface with the QWCL layer beneath, shaping the external field envelope during operation. The hull serves as both an aerodynamic shell and a field-guiding surface, maintaining a coherent bubble of controlled space around the craft. HL-HSPC's power system is built around 3 layers: baseline solid-state batteries for avionics and sensors, supercapacitors for fast response, and high-energy pulse power systems including low-torque quantum capacitor banks and QWCL TQCM subsystems. A supervisory energy management unit coordinates charge-discharge cycles, time-synchronized pulse delivery, and protective modes under fault or overload conditions, ensuring safe and efficient operation. Quantum wire capacitance layer, QWCL, forms both an energy interface and a field carrier layer. Constructed from densely woven CNT graphene filaments embedded in capacitor plates, it operates at high voltage and frequency, generating coherent M-standing waves across the hull. The QWCL distributes pulse power, amplifies and shapes the M carrier field, and creates the red stress field halo seen in visualizations. Low-torque quantum capacitor banks are the primary pulse reservoirs, housed in vacuum chambers on the lower deck. Operating at ultra-low pressures, they suppress dielectric breakdown and employ quantum wire plates for ultra-fast discharge. These banks supply high-voltage, short-duration pulses to the QGR and HFGR, supporting synchronized discharge patterns for mass-modulation cycles and providing a controllable energy budget for each resonance event. Thermoquantum capacitor modules, TQCM, convert thermal gradients into directed field effects. With one electrode cryogenically cooled and the other at ambient temperature, high-voltage, high-frequency pulses are applied across the gradient. This creates nonlinear M, thermal interactions, generating directional stress-energy flows that feed inward toward the HFGR core, enabling lateral control authority and vectorization. In advanced HL-HSPC configurations, a cooled superconducting bus links capacitor banks, QWCL segments, and central resonator stacks. This reduces I2R losses during high-current pulses, ensures cleaner waveform integrity at high frequencies, and increases the effective Q for resonant systems. The superconducting bus is a configurable upgrade path, enhancing the craft's energy efficiency and performance. Core propulsion stack of the HL-HSPC is built around the tunable Q gravity resistor, QGR, high-frequency gravity resonator, HFGR, noble gas resonant cavities, sonoluminescent microdomain zones, and toroidal field emitters. These elements form a vertically coupled engine column anchored to the structural midline, working together to generate lift and control through mass modulation and field resonance. QGR modulates how strongly the craft couples to its own inertial mass. Using metamaterial coils, spintronic arrays, and integrated gravimeters, the QGR can operate in high Q mode for reduced inertia and agility, or low Q mode for increased coupling and safety. It acts as the mass response governor, preventing runaway resonance and enabling fine-grained control of inertial behavior during flight. HFGR is the primary lift engine of the HL-HSPC. It features multiple noble gas cavities arranged in toroidal and axial geometries, driven by high-frequency M and acoustic fields. These conditions enable repeated sonoluminescent microdomain collapse, generating asymmetric stress-energy gradients and creating a downward-directed mass void, resulting in net upward force and lift for the craft. QGR and HFGR are synchronized systems. The HFGR generates the primary lift and mass void region, while the QGR regulates the coupling between the vehicle's mass distribution and the generated gradient. Spintronics control ensures phase alignment between QGR, HFGR, QWCL, and TQCM, forming the mass-modulated propulsion core of the HL-HSPC platform. To ensure flight safety and provide conventional envelopes, the HL-HSPC can integrate distributed electric fans or ducted thrusters for VTOL and low-risk operations. Reaction control jets or cold gas thrusters support attitude control in thin atmosphere or near space. These auxiliary systems serve as fallback options and provide a test harness for low-power resonance experiments during early flights. HL-HSPC's field geometry is defined by M carrier fields, gravity gradient shaping, toroidal mass void formation, and lateral vectorization via TQC and QWCL. The stability envelope and field bubble dynamics are carefully managed to ensure precise control and maneuverability. This advanced field architecture allows the craft to achieve lift, control, and inertial modulation through synchronized subsystems. HL-HSPC's avionics suite features a spintronics control grid, LiDAR radar gravimeter sensor suite, digital twin architecture, and autonomous resonance tuning system. Safety and fault mitigation logic are embedded within the control grid, ensuring real-time resonance control, sensor fusion, autonomous flight envelope stabilization, and fault detection during high-energy cycles. HL-HSPC Blueprint Series provides top, bottom and side views of the craft, highlighting the capacitor grid layout, structural segmentation, central dome radial truss network, lenticular curvature profile deck alignment, ribbing metamaterial hull tiles, HFGR geometry, annular capacitor band and axis zones. Each view is labeled in blueprint style, offering a comprehensive reference for archival, fabrication or simulation purposes. Engineering Schematics poster showcases the triaxial ribbing network, distributed quantum wire capacitor grid, precision-mounted resonator sockets, modular metamaterial hull tiles, and clean schematic overlays. This detailed cutaway is designed for engineering documentation, fabrication reference, and subsystem diagnostics, ensuring every component is clearly visualized and labeled for practical use. HL-HSPC's operational theory covers multiple flight modes: level cruise, transonic descent, and longitudinal control. The poster visualizes concentric field lines for the stability bubble, vertical control axis for mass-modulated descent, and lateral field shaping for maneuvering. Realistic craft details, including labeled upper dome, outer hull, and metallic surface, are highlighted against a sunlit aerospace backdrop. Safety is paramount in the HL-HSPC program. The poster features fault detection nodes, resonance containment barriers, emergency pulse dump circuits, autonomous shutdown logic, and a safety envelope field contour. These systems work together to maintain safe operation during high-energy cycles, with real-time diagnostics, containment logic, and autonomous fault mitigation, all governed by the internal HL-HSPC theory. Manufacturing and materials poster highlights metamaterial hull tiles, field actuator arrays, ultra-strong alloys, and carbon nanotube tubing. Each layer is visualized in a translucent cutaway, showing how the HL-HSPC's material architecture contributes to strength, field control, and modular fabrication. This poster is essential for engineering documentation, manufacturing reference, and subsystem integration. HL-HSPC's legacy is preserved in the attribution, legacy, and lineage poster. It features a central registry of authorship, historical resonator benchmarks, modular legacy nodes, upgrade pathways, and a formal credit to Cole James Hartman. This archival poster honors the technical lineage and innovation that define the HL-HSPC program, ensuring its contributions are recognized across generations. Deployment Scenarios and Strategic Roles poster defines the HL-HSPC's applications across tactical strike teams, ISR strike groups, and R&D programs. It visualizes the craft as a mass-modulated rapid insertion and exfiltration vector, a high-agility field camouflage platform, and a testbed for advanced field geometry experiments. This strategic overview aligns with the internal theory and hybrid innovator signature tone. Telemetry, Data and Simulation Systems poster showcases the Triaxis Telemetry Suite, HL-HSPC data archive, and diagnostic simulation models. Real-time positioning, envelope dynamics monitoring, flight logs, and AI-augmented interfaces are all visualized, supporting autonomous diagnostics, fault injection, and replay-based optimization. This infrastructure is vital for ongoing development and operational excellence. Ceremonial Registry and Archival Protocols poster is rendered in neon-lit ceremonial style, highlighting the central dome, authorship seal, archival beacon, legacy attribution ring, and historical subsystem registry. This poster is designed for legacy preservation, ceremonial documentation, and archival continuity, honoring the full HL-HSPC lineage and hybrid innovator signature tone. This extended cutaway poster provides a photorealistic, labeled view of the HL-HSPC's internal systems. Each subsystem is clearly marked, from the quantum wire capacitance layer and thermoquantum modules to the capacitor banks, gravity resonators, metamaterial hull, and spintronics grid. Cole James Hartman's name is prominently displayed, anchoring the program's authorship and innovation. This visual serves as both a technical reference and a tribute to the program's leadership.